Hello everyone, and welcome to our webinar on modeling nonlinear magnetic effects in COMSOL Multiphysics. My name is Arpad Forberger, and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at the basics of how COMSOL and an AC/DC simulation. I will walk us through some models to give you a chance to see the software up and close and see how it might help you in your work. If you have never used COMSOL before and you want to learn how it works, my presentation today should help answer those questions. Today's agenda will look like with a general overview of the software itself, how the COMSOL environment looks like, and then I will show you how it's done during live demos. I will demonstrate some features of coils, what kind of coils are available in COMSOL Multiphysics. During a model, I will show you how to set up coils with linear and with nonlinear material models. And at the very end, I will mention some further resources where you can find more information, including full-length webinars that contain more technical detail than what we will have time for today. Today's presentation is really meant to be a quick intro to what the software is, but we have many resources available if you are interested in learning more afterward. COMSOL is a multiphysics modeling, simulation and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. The model we will look today solves for current-driven coils and other magnetic and nonlinear magnetic effects. Once you have completed your simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics and chemical simulations, as well as several multi-purpose models and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And today's webinar is focusing on the use and the features built in the AC/DC module. We have several different components to the COMSOL software. Right now we are looking at the model builder in the COMSOL desktop, which you will see live in a few minutes. The model builder contains the tools for controlling physics, mesh, materials, and study settings. Highlighted in this image is the section of the ribbon that gives you access to the application builder portion of the COMSOL desktop, which contains the tools for building a customized user interface around your model, or what we call an application. Because, as I mentioned earlier, once you are finished with a simulation, you may want to be able to share the results with a colleague or a customer without sharing your entire model. The application builder will let you build this user interface around your simulation, and we will show it later on. Then to share it with someone who doesn't have COMSOL installed on their machine, you would use a local installation of the COMSOL server, which makes the app accessible either through a COMSOL client or a web browser. What's really powerful about this is that the person that you share the application with doesn't actually need to have a background in COMSOL, numerical simulation, or the relevant physics. For instance, you might share it with a colleague who doesn't have your modeling knowledge, but who can use your app to run quick virtual tests and check different designs. The following coil features are available in COMSOL Multiphysics. It can be a single turn coil with a solid cross-section, whether it's a 2D or a 3D model. It can be axisymmetric, you can include AC or DC fields. For 3D model you can include DC only. Or it can be a multi-turn coil. It means you cover a bunch of wires together, whether it's a 2D or a 3D model. Okay, for single conductors, it can be an open type, a closed type, or a series connected multiple conductors. You can reduce models and computational time with using symmetry conditions. For homogenized multi-turn coils that we are looking into in the next model, you can use a linear coil, a circular coil, a numeric coil. That's what we are going to use in a few steps later. Or it can be reduced by symmetry conditions. And as always, you can define your own coil, whatever the shape and the function of it is. Or you can use the lumped port boundary condition to create coils inside COMSOL Multiphysics. And now, if we go into COMSOL itself, we can start with the model wizard, with a 3D model, with the magnetic fields physics interface. And first we want to solve for a frequency domain study. So if we go to the next chapter, then we can select what kind of study type we would like to use for this model. So first, we would like to use a frequency domain calculation. To reduce computational time and effort, I will import the geometry sequence from a previously defined and solved model. So you will see the geometry in an instance. Okay, and here it is the geometry itself. We will use this for today's demonstration. Here we have different domains. So here we have the surrounding air domain, then we have these cylinders for the second coil, we have another cylinder here for the first coil, and we have this core here that will be used during our simulation, including linear and nonlinear material models. So these are the computational domains that we are going to use during this model. Okay, so let's add the materials. So materials, we need air for the surrounding domain. Then we can add some blank material for the coils. So we can simply select the coils. This is one. And we have another coil here. Okay, we can use the default values here. And then we can add the soft iron. This is also from the built-in library, so we can use this material properties for the internal core. And as you can see, we can add some relative permeability. So here, and literally wherever in COMSOL you can click, you can put a number there, you can put data from measurement, it can be a function, it can be a user-defined function, it can be a MATLAB function, whatever you would like to use here. Okay, so we have set up all the materials, we have the air domain, then we have the materials for the cores, and we have the cores material properties set up here. And if we want, we could add in the basic field, in the permeability, if you would like, you can introduce anisotropy or any matrix valued properties. So it can be any value, not just a scalar value. So if you are interested in, let's say, in frequency domain calculations, you can even put an imaginary part here that can be useful for frequency domain calculations. So the geometry is set up, the materials are set up. Now we go into the physics setup. So we could simply enable coil features. So first we will set up one coil here on the right side. Okay, we have selected the domains, and then we will use homogenized multi-turn feature because we want to model a bunch of wires together. The coil type is numeric, so COMSOL will need to solve for the current distribution inside the coils, and an excitation is a current excitation. Okay, number of turns, let it be 90. That's all. And from the geometry analysis, because we cut half our computational domain to reduce computational effort, so we need to put a factor of 2 for the coil length multiplicator and for the area as well. And then we need to set up the input and the output of our coil feature. So where current goes into the model, this is the input, as you can see here. Okay, and we can set up an output here. That's it. So our first coil is set up. Then we can simply duplicate and remove the selection and select coil 2 on the left hand side. Okay, so this is our second coil with the same properties, but we can put a phase shift here, minus j times pi over 2, so we can include this shift, this nice shift here, and from the geometry analysis we can select the input cross section, which is here, and we can select the output, which is here, and that's all from the coils selection. Okay, so that's all for the properties. Currently we have these relative permeability, so between the B and the H field we have these relation together. One thing is missing here because we are using quite low frequency. So if we are going to here and we can set up the frequency, which is 10 Hertz that we are looking into. So for low frequencies, for numerical stabilization, it's nice to add the so-called gauge fixing here for A field. That's really nice, and you can do this in COMSOL to increase robustness of your computations. So 10 Hz is quite low, so we can add this extra numerical stabilization to our model. So we have coil 1, coil 2 with a nice shift here, and that's all. From the mesh part we can use the physics controlled mesh, nothing special. And from the frequency domain, the frequency that we are looking for is F. Okay, and one thing is missing because we don't have the full coil, so we cut half to reduce computational effort, and because we set up that it is a numerical coil, we need to ask COMSOL first to calculate the current distribution. This is called, and this is solved during this coil geometry analysis. So this is step 1, and then we can go on with the frequency domain solver. To speed up calculation, I open up the currently solved one. Okay, so if I open up this one, now we can go on with plotting the results here. Okay. Where is it? Sorry, time dependent. It's here. Okay. So if we solve and we open up the physics here, we can see the solution here. So this is the norm of the magnetic flux density. So here we have some higher values, close to 1.6 Teslas, and this is true for this F0, 10 Hertz excitation frequency. So this is the frequency domain calculation, but go further and we can add other nonlinear models, like if we go back to this magnetic fields formulation, we can add an Ampere law, a second one, into the internal core here, and as you can see, here the constitutive relation is set to HB curve. So if you have your HB curve, whether from measurement or you have some other data from literature, you can include that as well in COMSOL Multiphysics. And here, if you go to the material properties, you can see that these curves are defined here. So you can simply plot and you can see how these correspond to each other. So this is the pH curve. So we can zoom in to have a better look how it's look like. And if we solve for this kind of material model, then we can see the hysteresis and the loop between the B and an H field. And of course we can also plot the shape of the magnetic field during the time-dependent calculation. So for this HB relationship we need to use a time-dependent simulation because it's a nonlinear model, so we cannot use the frequency domain calculation right now. So here in the coil features we simply replaced the excitation with the sine function. So we multiply the peak value with the sine of 2 pi, f is the frequency times t. So in this sense we can use this in a time-dependent simulation, and one thing is that we set up this HB curve relationship in the internal core to include saturation and the hysteresis loop between the B and an H field. So here we have a second study for time-dependent calculation, and here we are going from 0 to 200 milliseconds, so it's 2 periods, and then we can see the results, how they look like. So let's start with the magnetic flux. I already prepared this plot for us just to take a look at this, so we don't need to wait for solving it. And now you can see the blue sign, a simple sign that goes for the frequency domain calculation with the default linear correlation between the B and an H field. And here you can see the green one that corresponds to our nonlinear HB curve correlation. And here you can see some saturation appears here. And what's nice that if you create an FFT on this, you can see the main frequency and the harmonic frequencies as well. So here I created an average operator that will create an average of the magnetic field on these little boundaries. So we are interested in the magnetic field and the saturation effects in these boundaries. So this little boundary belongs to the internal core, which has this nonlinear BH curve. So we can use this average operator to plot our variable. So if we create a 1D plot group and we select an average 2, then we can create an interpolation for one period. If it may be too fast for you, that's no problem because we record this webinar, so later on you can reuse anytime you want, so you can receive this one and you can see how it's done in a smaller way. So from 100 with one step size to 200, and we can create a global plot of the magnetic field MF dot, let's say by, the y component, it's in Teslas, and X data is a frequency spectrum, and we could scale this one. So here we can simply create an FFT on our function, and you can see, so we have this 10 Hz, the main driving frequency of our excitation, and because of this nonlinear material you can see there are other frequencies that will appear in the response in our material. So that's one nice thing that you can see, create quite easily FFT calculations on any signal in COMSOL Multiphysics. Another thing that you can simply plot the B and an H field next to each other. So here you can set up some kind of loop, some hysteresis loop here. So this is from the same average operator, so we are plotting the B and an H field on the same boundary. So if we go back here, so this is the boundary that we are speaking of, this central limbs little surface. So we are plotting the values on this surface. So if we are plotting the B and the Y field, H field so we can see this loop between the two components of these vectors. So this is how you can plot and how you can add the materials in COMSOL Multiphysics. It's easy to add the fast Fourier transformations to set up. And yes, we have limited time, but we have one question that I would like to address here. So how and what kind of other nonlinearities can be introduced in these materials? So if you go back to the physics settings, here I've showed you the HB curve. You can define your own one, but there are other ones. So you can include an effective HB curve if you are interested in more in that kind of calculations. And the Gillard-Terton model is also available that can be included in your model. In this sense, if you switch to this model, there are some nice parameters that can you set up, whether from literature or you have those properties from measurement or from other calculations. So these are the available relations between the B and an H field, and that can be interpreted in COMSOL Multiphysics. So in the follow-up email you will get the link for these kind of simulations and models and for the webinar itself. And to wrap up my presentation, I will show you some other links and useful infos where you can get more. So if you go to COMSOL's website or our website at gamaxlabsol.com, you can get a free trial for the software itself, so you can try out all of these models and properties. What you can do here, you can have lots of videos, webinars, tutorials, how to access and what you can do with these built-in models, and you can browse the model gallery for more models. At the website you can find much more materials and ready-made applications that you can dive in, or you can simply drop us an email or visit our website to ask for more information. If you need a special on-site demo or you have a very specific physics you would like to include in your simulation, feel free to contact us at any time. So this was our very short webinar on this kind of nonlinear effects, magnetic effects in COMSOL Multiphysics, with including this HB curve and how to plot between different components of the field and how to create some little FFT on the field that you can include. And I switch back to this one, so you can see the blue one is the frequency domain solution and the green one is the HB curve material model where we have saturation effects. And this is one little step that you can do in COMSOL Multiphysics for this kind of coil calculation. So I close up my presentation. Thank you for your time, and if you need more information, as I said previously, just drop us an email or visit our website. Now I thank you for your listening, and I hope you enjoyed the presentation. Have a great day and see you in our next webinar. Thank you and bye.